All right, hello everyone. Today is our class number 18, and today we're going to talk about decision trees. So we use the abbreviation DTs, and decision trees are super powerful. These are one of the simplest decision trees themselves. Machine learning models out there, it's like KNN, the model is super simple, but unlike KNN, decision trees are highly interpretable. So this is the power of decision trees, because they're even more interpretable than linear regression. And because it's easy to present the decision trees to clients when it comes to finance, and it's easy to interpret the information. And so for that reason, we're really interested in decision trees in general when it comes to finance. Okay. And the decision trees are supervised machine learning models, and they're non-parametric. It means that you're not imposing any restrictions to the functional form for our predictions, right? So the f hat of x that we are trying to estimate at the end of the day, we don't impose any restrictions. So these are non-parametric models. So you can guess, like KNN, which was non-parametric, it can be super flexible at the end of the day, and it can be easily overfit the data. So we have to do something about all these things. So we want to take the positive parts of decision trees and then fix the caveats of decision trees, right? So the positive ones are, it's interpretable, it's very flexible, it can be very flexible, but the caveats are, at the same time, you know, the accuracy is not good when it comes to comparison with other models, like even the SVM, support vector machines, right? So the concept of decision tree is very simple. I guess everybody is familiar with that. You know, decision trees are sequences of some questions that basically are asked to seek the basically to partition the data sets into homogeneous groups, right? So imagine that here we have in this example, we have a classification. Let's say we have two features, X1 and X2, and then we have two classes. At the end of the day, the data is like this in 2D. So we have class blue and class red, right? Imagine we know nothing about the decision trees. So if I give you this information and then I ask you to, can you come up with a good classifier? So what are the options? The options are, you can make a linear classifier like this, right? So a linear regression model, or you can do logistic regression. We can, for example, come up with the SVM and then using the RBF kernel. So maybe we can come up with something like this and then make sure that we have a couple of landmarks, and then we can separate the data like this. Or we wish we could do something like this, right? So this is really neat. Right? If I can divide, at least in 2D, the data using some squares, it's going to somehow perfectly do the job for us. And this is what the decision tree is able, right? So the decision tree is going to use some squares, you know, divide it, in this example, divided the two-dimensional data into a bunch of squares and then classify them, right? As you can see, this is obviously nonlinear. The classifier is nonlinear, right? And so how do we construct a decision tree? So this is a big question that we're going to target today. And as I said earlier, the decision trees are sequences of simple questions. So for example, in this example, if X1 is greater than split, this is our cutoff point, we call it split. If it is greater than S1, then if yes, we are in the region 1. Let's call it R1. If no, we can come up with another cutoff. Let's call it S2. If X2 is greater than S2, if the answer is yes, we are in this region. If the answer is no, we are in this region, right? And then at the end of the day, we want to make some predictions. So what are the predictions? If we are dealing with a qualitative target variable or categorical target variable, like in this example, which is blue versus red, we look at the majority votes, right? So the most common occurrence of the classes, right? So here, for example, what's in R3, what is the class, red or blue? The class is red, right? Does everyone see that? In R2, what is the class? Blue. And in R1, what is the class? Is going to be blue, right? So we look at the majority vote, or the majority of the class within that specific region, right? And so this is classification. However, if the target variable is continuous numbers, right? It's quantitative and continuous number. And imagine the blue ones are just some numbers close to each other, right? So for example, I don't know, I'm just making up some numbers. So these are, we can color code the blues and reds into dark blue and let's say pale blue, something like that. And the darker the observations are, the higher the number. Let's say something like that. Then we can get, let's say, I don't know, 10, 11, 5, and etc. Well, let's call it 15, and etc. And here, let's say these are the very smaller numbers, a scale of 1 to 3.5, and etc. Right? If the target variable is something like this, and we can color code it with I don't know, for higher, with greater numbers, maybe the darker, and then the predictions are going to be some average values. So in region 1, let me actually clean up here. In region 1, the predictions are going to be the average value in region 1, right? So average value of all these dots in region 1, and these are continuous numbers, right? In region 2, these are the, let me be precise. These are the, I can calculate the y bar of 2, and in region 3, I can calculate the y bar of 3. So depending on the type of your target variable, if the target variable is qualitative, we call it a classification tree. If the target variable is continuous, we call it the regression tree, right? And so in R1, the predictions of the model is going to be y bar 1. In region 2, the prediction of the model in this simple example is going to be y bar 2, and here y bar 3. So is the distinction between classification trees and regression tree clear? The algorithm is going to be exactly the same. So there are some slight nuances when it comes to splitting criteria, but the algorithm, the steps are exactly the same. All right. Okay, in terms of roadmap where we are, again, we're still in the, actually this is going to be the last supervised set of models that we're going to go through, decision trees and their extensions, right? So we're going to work with one tree and then extend the tree to multiple trees, call it random forest, and change the way that we grow trees, we call it boosting, right? And so these are very powerful machine learning models out there, and these are historically the winners of many famous competitions out there, including Kaggle competitions and M-series competitions. So I highly encourage you to deeply understand the theory behind the tree-based models in general. So the tree-based models are used for both classification and regression. So this is the advantage of these models. And we can have, it's not restricted to these 3 ones, but these are the ones that we cover in the class. So the first one that we cover is going to be decision trees. And we're talking about a single tree. Right? If I use a single tree and apply it to the data, we call it decision tree. And then it can be classification trees or regression trees. Then we will talk about the caveats of, so the power, the advantages and disadvantages of this decision trees. And if we like the advantages, we want to improve the disadvantages. So that's why we go from decision trees to use a concept like bagging and random forest. So basically instead of working with one tree, we work with thousands of trees in the hope that we can reduce the variance of estimator, right? So we know that we can reduce the variance of estimator, and bagging and random forests are able to do that for us, right? Then boosting is even more advanced than that. So in boosting, we hope that we can keep the bias small and at the same time decrease the variance as well, right? And the reason that boosting is able to do that is because we are, let's say, we are growing the trees in a very smart way. We will talk about the mathematics behind the boosting in a couple of, in next 2 sessions, but that's the general idea. So these are we call all of them tree-based models, right? So today we're going to cover the decision trees. Okay. So what do we do? In part 1, we talk about we make sure that we understand all the definitions. Then we talk about decision tree criteria. This is really important, right? So this one, we have seen MSE before, we have seen error rate, but Gini index and entropy are new things, and we need to understand why we have to go beyond error rates, because why error rate is not a good criteria for us to expand the tree. We'll talk about Gini index and entropy as 2 of the most practical criteria for splitting the tree out there when it comes to classification. Then in part 2, we talk about how decision trees actually work. We will see behind the scene of a regression tree and classification tree. There's a huge overlap between the algorithm when it comes to regression versus classification. Only the decision tree criteria is different. For regression, we're going to use MSE. For classification, we're going to use actually not error rate. We're going to use Gini and entropy. So, but we'll talk about these definitions. Then in part 3, we talk about what does the concept of pruning a tree mean? Why do we need to prune a tree when it comes to the trade-off between bias and variance? So conceptually, why it is a good idea to prune the tree, and what are the caveats with pruning a tree? Then we talk about hyperparameters. As I said, the decision trees are supervised and non-parametric models, but there are lots of hyperparameters that they can tune. Okay, there are lots of hyperparameters, and so this is not necessarily good news, but on the positive side, you can make the model super flexible. But on the negative side, the model can overfit because it's super flexible. But we will talk about all those hyperparameters as well. Finally, we will conclude by going over pros and cons. So this is going to be our segue to random forest, because we like the advantages and we want to improve the disadvantages. So we'll see how we can do that. And then finally, we talk about a bunch of applications in finance, which is a lot, especially decision trees, even though they are super simple, and even though the accuracy is not good enough, the performance is not good compared to other machine learning models, but still we use it because at the end of the day in finance, you want to sit in front of a client and then convince him or her that why this happened, or basically you want to make sure that you can communicate easily to the client. So you need an interpretable model. Okay. All right, so let's start with the definition. So the formal definition for a decision tree is, these are machine learning algorithms that progressively, so the key terms are this, progressively divide the data into some smaller data groups based on descriptive features. So imagine in this example, we have the features are height versus weight. This is very simple example. And maybe many people cannot relate to that, but on average, this is true, right? And so the algorithm progressively is going to divide the data into smaller groups until reach sets that are small enough to be described by some label. So that's why this is a supervised machine. Because at the end of the day, I'm gonna start splitting the my feature space here. Let's say I do something like this and do something like this. I continue this splitting to a point that these are homogeneous enough. Mathematically, we can quantify these things, and we'll talk about them, right? So let's say, or there's this stopping criteria. I say that, okay, at the terminal node, which we're going to cover the definitions, so I need to have this amount of observations in each node at the end of the day, right? Decision tree apply a top-down approach to data, trying to group and label observations that are similar. So this is basically what decision trees are designed to do. It's a top-down approach. It starts from the entire data, and then to ask some sequences of questions to narrow down the data. And at the end of the day, we come up with some homogeneous observations within groups, right? So imagine this is my first split. So I say if height is greater than 6 feet, call them male. Imagine the blue ones are male and the red ones are female, right? So the first split, if you know nothing about decision tree algorithm, right? At the end of the day, there are two questions that you have to answer. Which feature to start with, right? Should I start from weight or height? So this is the first question. The second question is, where should I put the split? Where should I put the cutoff, right? So visually, when you look at this, but let's give it a try, actually. Let's slow down and give it a try. So which feature do you think I should start with, height or weight? So why do you think weight? So if I start with weight, it means that I'm gonna use the split. So this is going to be my weight, right? Now, if you look at the top data versus bottom data, so there are lots of misclassifications going on here. Okay, so I have to, at the end of the day, I have to quantify it somehow, right? So maybe this is a good split, maybe not. I don't know yet, right? But I'll look at my alternatives. Right now, I know if I start like this, there's going to be a lot of misclassification at the bottom part. Do you agree? Okay, so I would say that maybe starting with weight was not the ideal case. Again, visually, we have no idea. We have to quantify all these things. But visually, I would say maybe weight is not good. But if I look at height, now there's still a lot of misclassifications going on here, right? How do I know that which one is better? I need a metric. Sometimes visually it makes sense, you can do that, but sometimes you really cannot, right? So I need to come up with metrics. That's what we call the decision tree criteria that quantify these things for me. Okay, so which feature to start with, height versus weight. So in this example, I'm going to give you the answer, and it seems that we would be better off if we start with height, and then in the second split we go with weight, right? So we would do something like this. We ask the question, if height is greater than 6, if yes, that's male. And guys, do we have a female with height greater than 6? Of course we have, right? So there is one, and percentage-wise, think about it in the entire population. This I guess makes sense, right? I have 40 observations here. 1/40 is greater than 6 feet. So maybe again, maybe we can relate to this data. But so this is male, and if the height is not greater than 6, we're going to come down. I'm not happy with this entire region, right? Because there's going to be a lot of misclassification. I have to split it even further. So let's go ahead and split it using weight. If the weight is greater than 180, if yes, so we are here, we're in this region. And male, if the weight is not greater than 180, this is pounds, then we are in this region. It's female. Does that make sense? At the end of the day, again, visually, I'm glad that actually, David, you said weight, because I just wanted to make sure that sometimes visually, it doesn't necessarily make sense. So you have to go down the tree. If I started with weight, something like this, then the second split would be like this, and then this part is going to be one region, one region, one region. And I can count the number of misclassifications and see which one is doing a better job. Okay. All right. So this was an example of classification, by the way. But we're going to go over the details of regression first and then classification. But before that, let's quickly review some terminology. Okay. So when the target variable is are real numbers, so we are dealing with regression trees. When they're categoricals, we're dealing with classification trees, right? And let's quickly clear some terminology. This is our root node. So the root node is the beginning of the tree, right? So this is the root node. Then we come down the tree and we have to split the data, right? So this is what splitting means, right? So split, divide a node into 2 or more, let's say, subnodes, right? So this is one node. We also call them, so this is node. It's going to, so split is going to make that node into 2 or 3 or 4, whatever number of new nodes, right? So the new node, so this is what we call splitting. And branch is something that connects the nodes with each other. So this is one branch. This is another branch. Connecting the nodes, right? So this is a branch. Okay. Then decision node. So the decision nodes, or also we call them internal nodes. So these are nodes that something comes into them and something gets out of them, right? So that's why we call them internal nodes. So they receive something, there's some input and some output. The difference between internal node or decision node and root node is that there's no input here. This is just at the beginning of the tree, at the very top level. Okay. Then leaf node or terminal node. So the terminal nodes are at the very bottom of the tree. So these are, so we call it terminal node. And so the way that we distinguish it in a very bushy tree is that there's input, there's no output, right? Something comes into it, but nothing gets out of it because these are the terminal nodes. Then subtree. So subtree is going to be a part of the entire decision tree, and we have to make sure that in a subtree we have to have a node and terminal node. So this is a subtree. This is a subtree. What about this one? Is this a subtree? This one. No, right? Because there's an internal node here, and the subtree, we call it tree as long as there are some terminal nodes, right? So this is not a subtree. This is not a subtree. Does that make sense?
So it can't have an internal node?
No, it can have. No, that was not the distinction. Distinction is that, so this is a subtree, right? It can have internal node, but it must have terminal nodes. Should not end up with, this is not a subtree.
Yeah,
because of this internal node, yeah. If this is what you were saying, yeah. Okay, then depth or level. So the level is the longest path from the root, longest path from the root to the leaf node. So which one is the longest? So maybe this one, either this one or the other one. That's the same. So what's the level? 1, 2, 3. So here in this example, the level is 3. The longest path from the root node to the terminal node. Okay. And then finally, pruning. So pruning is removing subnodes from a tree. So the process is called pruning, right? So if I remove, for example, this subnode and replace it with a terminal node, so let's call it leaf node or terminal node, then it would become this process is called pruning. I'm trying to prune back the tree. So let's say we have a very bushy tree and there are some advantages and disadvantages with that bushy tree. We need to prune it back. Okay, so this process is called pruning. Okay, are we good in terms of definitions? All right. Okay, so this becomes the beauty of, well, actually, this is a backbone of how decision tree algorithms are working. So we start asking this question. Imagine this is a data. Imagine this. There's a delay between what I move here and what you see. This is our data set, and very, very simple data set, right? We have 2 features and 2 classes, blue and red, and 10 blue observations, 10 red observations, and these are the train set. And imagine you want to decide that which feature should I start with and where to put the cutoff, right? These are the most important questions in decision trees. So we put it like this. Let's make it more formal. Which split adds the most information gain? And i.e., this is also called the minimum impurity. So what do I call by impurity? So guys, look at that. If I use this split, I have 2 regions, right? Region 1, region 2. Can you say that region 1 is pure? No, right? It's very impure. And if you look at the numbers, so I have 10 observations here, 5 of them are blue, 5 of them are red. Actually, the impurity is going to be max here because it's completely random, 50-50. So if I use this split, let's call it vertical split, the impurity is maxed, right? And both on region 1 and region 2. So here on region 2 also the split is max, the impurity is max. So the decision tree is going to move ahead and continue splitting until, when we get the most information gain or the minimum impurity, right? So this is not a good split. What if I go ahead and instead of this vertical split, I use a horizontal split, right? What about this one? Can you tell me what is the purity in region 1? 100%, right? So the purity is, this is, in the top part, they are all blue, and the bottom part, they're all red. So I show you the extreme cases, right? So usually in real world, there's something in between, right? So, but in extreme cases, it is obvious that the vertical split was not a good one, and the horizontal one was a good one. And now let's try to quantify these things. Again, visually, it's easy, but mathematically, let's see how we can quantify these things. You already answered the question. You basically answered this question that, is this class pure? Is this region pure or not? So let's see how we can quantify this word, purity. So there are some indices out there that we use. They are called impurity index, and we have 3 different of them. Let's see. But before, well, actually, let's talk about them. This was an example of classification, right? If I had regression, I can use MSE. So imagine, let's go back. Let's talk about the regression first, and then we'll talk about classification, because the regression is really easy to understand. So imagine these blue dots and red dots are numbers. They're not labeled, so they're numbers, right? So for example, again, blue ones are higher, 10, 11, I don't know, 8, 9, very close to each other, right? 8.5. And the red ones are smaller, 1, 2, 2.5, 3, 4. Does that make sense? For both sides. And these are maybe different numbers, 12, 10, and etc. And then if I use this split, if I use the vertical split, what is the prediction of the model? The prediction is going to be the average of these values. Do you agree? So let's call them region 1. What is the prediction for region 2? The average number of all those numbers, right? So let's say I get the average number is 5, I get 5.6. Is this good? Is this a good classifier? Is this a good, let's say, split to start with? The answer is no. Why? Because these are if I calculate MSE, mean squared error, MSE is going to be super large, right? The observations are far from the average. Let's say that here is the average. Do you see what I'm trying, where I'm trying to go with that? So MSE is going to be able to basically capture this problem of how should we split? Should I use vertical line or horizontal line? I compare the MSE, and so I use the vertical split, calculate the MSE on the left and right, and add them together, I get a number. Then I will go ahead and use a vertical split, sorry, horizontal split, and then again report the MSE, right? So let's say here is going to, the Y bar is going to be around 10, Y bar is going to be around 3. Does everyone see that? Now if I calculate MSE, it's going to be a lot smaller. So region 1, region 2, it's going to be a lot smaller compared to the previous case. And then I add them together, compare this summation with the previous summation. Which split give me a smaller value? The horizontal split. Does that make sense? So for regression, it's very straightforward. So for classification, we're looking for something like this. We want to quantify this idea of information gain or minimum impurity. So there are the criteria, the classification tree criteria are error rate, entropy, and Gini index, right? So all these things control how a decision tree is going to decide to split the data. This is real. Again, guys, this is the gist of the model. If you understand this part, you're good to go, at least for the decision part, decision tree part, right? So now let's see what is the error rate, entropy, and Gini index. In a nutshell, we call them impurity index. So if they're 0, it means that the impurity is 0. If they are maximum, it means that the impurity is maximum. So for example, you can at least, you already answered this question. So here, if I use a horizontal, let's actually, they all measure impurity. If I use a horizontal split, the impurity for region 1 is going to be what? Well, it's completely pure, so impurity is 0, right? So here, again, the impurity is going to be 0. So what does it mean? It means that if you calculate the error rate, you're all familiar with the error rate. What is the error rate for the blue class? 0. What is the error rate for the red class? 0. If you calculate the entropy and Gini, you haven't seen the formula yet, but it's going to do the same. Well, the formula is different, but the concept is exactly the same. So the entropy in this example is going to be 0, and Gini is going to be also 0. Why? Because we have a pure class. Both this split is going to divide the data into 2 pure classes. We love this split, right? Now let's see what's the mathematics behind them. So these are the formulas. At this stage, I will give you the big picture of the formulas. How do they do the job? And when it comes to classification trees, I put together a numerical example, and we're going to slow down and calculate all those numbers together, right? But for now, let's look at the big picture and the definitions of entropy and Gini index. So entropy measures the impurity or randomness or also uncertainty in the data, right? As you can see in the previous example, if I use a horizontal split, the entropy is going to be 0 because there's no uncertainty in this data, right? Are we good? Gini index, however, again, conceptually they're telling you the same story, but mathematically they're slightly different. The definition for Gini index is that it measures how often a randomly chosen element would be incorrectly labeled. So I want you to think of this statement. How often a randomly chosen element would be incorrectly a statement. Now let's go back to the slide. Answer that question for me. How often a randomly chosen element, let's say this element, is wrongly misclassified? So what's the answer here? 0. If I pick any of the elements here, they're not going to be misclassified at all. Does that make sense? Either for blue class or red class. So this is the definition of Gini index. Okay. So for both entropy and Gini, 0 express all the elements belong to a specific class. So that's what we call pure. And so here's the equation. Again, for now, I want you to get the big picture when it comes to the classification models. We're going to work with a numerical example. So this is a formula for entropy. It's going to be minus summation of Pj multiply log of Pj. So that's why I told you that I don't like you use my initials. So this is one example, Pj. What is P of j? P of j is a probability of, let's say, class J in one of the regions, right? So for example, here is the probability of class blue in region 1. What's the answer? 1? 100, right? What's the probability of class red in region 2? Again, 100%, right? These are some examples. If I go, well, actually, let's do that. If we go with this one, with the vertical, split. What's the probability of class blue here? I have 5 blue, 5 red. What's the probability in region 1? What's the probability of class blue? 50%? Yeah, exactly, 50%. What's the probability of class blue in, let's say, region 2? Again, 50%. Are we good? Okay. For red as well, the same story. Okay, and so what entropy does, it's going to go ahead and multiply P and log of P. We'll talk about why log, what are the properties, but again, in next section. Multiply these two numbers for each class, add them together, right? So multiply this probability of, in the previous example, class blue, multiply to log of class blue, probability of class blue, plus probability of class red, multiply the log of the probability of class red, right? And why do we have a negative sign? Because the log of a number less than 1 is a negative number, so we multiply by negative to get a positive number. You want to minimize this thing, okay? So this is how entropy, well, again, it's at the end of the day, it's going to give me a number. If that number is 0, what does it mean? It means that we have complete purity in that split. If the number is large, the larger that number, the worse, right? It's bad news. So the goal is to minimize these things, to minimize this criteria, right? And look at that. If the class is pure, if our classes are pure, do you agree that the probability of blue in the previous example converges to 1 or 0, depending on how we are looking at the data, right? So in the horizontal one here. So here the probability of blue is 1, here the probability of blue is 0, right? So if these probabilities are converging to either 0 or 1, you're moving toward the pure classes, right? So if you move toward the pure classes, the entropy is moving to 0. And this formulation is enabling us to do that, right? If P goes to 1, so this is 1, log of 1, 0. Then if P is equal to 0, multiply a number, is going to be 0. So do you see that how it's doing the job? This formula is mathematically doing the job for us. If P's are converging to either 0 or 1, our entropy index is going to be 0. So this is the definition for entropy. For Gini, it's the same story. We're going to do 1 minus summation of the probabilities, right? Again, you can do the math. If the probabilities are, if one of them is going to 1, the other class is going to 0, right? So if I do one of them goes to 1, the other one goes to 0, so it's going to be 1 squared plus 0 squared. So 1 minus 1 is going to be 0, right? Mathematically is going to enable you, if the probabilities are converging to 0, the Gini index is also going to 0. So this is what we see here. So actually, this is a really interesting visualization comparing different criteria. So we have entropy. Where's my cursor? Do you see the cursor? Yeah. We have entropy, and entropy is scaled. I'll talk about how do we scale it. And then Gini impurity. Gini index, we also call it Gini impurity, and misclassification error. As you can see, the misclassification error, the blue dashed line, by the way, all of these criteria will satisfy the condition of if the probability, look at that, this is a probability of class in region, let's call it M. If the probabilities are close to 0 or 1, we get complete purity, and all of them are going to calculate this impurity index to be equal to 0. Right? All of them are doing a good job. The difference between them is that how sensitive they are in the change of purity, right? So the misclassification error, as you can see, it's less sensitive than Gini index, and the Gini is less sensitive to entropy, scaled entropy, and scaled entropy is less sensitive to this entropy definition that we have here. And by the way, this is log in the base of 2. If you do log to the base of 2, we call it Shannon entropy. This is originally, the entropy originally was defined by Shannon, and then For log of 2, we call it Shannon entropy. But in practice, we can replace that log of 2. We can scale it by, let's say, divide both sides by the natural log, so we get a natural log, right? So this is a scaled version. All right. So I want you to realize that in practice, the Gini index and the entropy, well, the scale version here, are going to be very close to each other, especially when the class is not pure. When the class is not pure, it's random. Well, basically, when the class is not pure, what does it mean? It means that the data is completely random, right? Your split is making the data completely random. If that's the case, these two, the performance of the two are very close to each other. And really, if you do cross-validation, for example, grid search cross-validation, changing these parameters, basically there's not going to be huge improvement. But if you're talking about the ends, then the let's say entropy is going to outperform the Gini when it comes to making a better split. Does that make sense? All right. So again, this was a big picture. We are going to do the calculate. We will see it over a numerical example how these numbers are exactly calculated. All right. So we're done with the definitions. Let's move on to the next part. So what is regression tree and what is classification tree? Basically, how does a decision tree work? We already know, we have a mathematical statistics in our hand that how a tree should make a decision on splitting the data. At the end of the day, I have to compare these numbers, right? I have to compare the MSE in different regions. I have to, if it is regression. If it is classification, I will compare either the Gini index or the entropy for different regions. And I'll work with the, well, we'll see how the algorithm is going to do the job. So we're going to start with regression trees. So let's go over the regression tree first. For this example, I'm going to use an example from the textbook, our main textbook, Introduction to Statistical Learning in R. And we're going to stick to that example here. So, and the example is about baseball salary. Let's say the features are number of hits and number of years. So these are the number of years that a baseball player has been playing in the field. And these are the number of hits per year in the previous year, right? And the salary is color coded from low. So the blue greenish ones are low salaries to high. Yellow reddish ones are high salary, okay? So guys, this is X1 feature, X2, and colors are my Y variable, right? The target variable. So this is color coded. So here, salary is kind of low. Here, the salary is kind of high, okay? So this is a setup. Is there any question about the setup? So this is our regression, okay? So now let's go ahead and try to answer these two questions. So we're going to start visually. I want you to think about these two questions and try to give the answers by looking at this graph. Which feature to start with? So what do you think is the answer? Years or hits? Which one is the better? Years. Years. So Abraham is saying years. Why?
Because you can see a distinction between the low salary and the high salary.
Yeah, because if I look at years and then if I go from years, for example, 0 to 20, the color is changing a lot, right? So it means that I can split and say that, for example, less than some specific years, the average is going to be closer to each other and etc., right? But if I look at the hits, when I go for any specific level of years, when I go from 0 hits to high level of hits, it seems that the colors are the same. So that's not necessarily a good split, right? So as Abraham pointed out, maybe years is going to be, so the answer is years. Again, we're doing all these things visually, and then we will see how decision tree mathematically is doing all these things behind the scene, right? So second question, where to put this split? Can you give me a number? Look at the years variable and give me a number. Like an eyeball. 5? Does everyone agree with 5 or something? Yeah, around 5, a little less than 5, maybe here. Does that make sense? So maybe, I don't know, 4 point something. Does everyone agree with this split? So this is going to be relatively a good split, right? Because look at that, when yours is less than 4.8, all the colors are kind of close to each other. So when I get a Y bar, it's not necessarily a bad thing. And for this part, however, I have both yellow, green, blue, greenish, and yellow, red, right? So maybe I'm satisfied with the left region, but are you satisfied with the right region? Most probably no, right? If you want to continue this split, Let's actually do that. It's a fun exercise. Let's go ahead and say that, I want you to focus on region 2. How do you continue? Are you going to start with years or hits? Again, years? So who says years, who says hits? Which one do you think is a better variable to start with? Only focus on region 2. Ignore this part. Okay, years, raise your hand. Hits? Okay, so everybody says hits, right? So we got for the second step, we got our answer, so the hits. And what is the cutoff? What do you think is a good cutoff for that? About 100, right? Does everyone agree? Okay, so about 100. So maybe we will end up with this, right? So we have R1, R2, R3. Maybe visually we will end up with something like this. Can I continue further? Of course you can, right? So again, as long as there's no stopping criteria, the decision trees are going to go way down the road and eventually put one observation at each terminal node. So this is absolutely overfitting, right? But for example, if I want to continue the process, let's focus on R3. So again, should I use, I don't know, maybe I can do maybe something like this. Maybe, I don't know, I'm just guessing. And when it comes to R2, we don't know, maybe coloring. This is becoming harder and harder, right? So maybe I cannot trust my eyes anymore. So we have to use mathematical formulas and see what's the best split, right? This is exactly what we're going to do. Okay. Interpretation is very easy. And this is the power of decision tree because it's very, very interpretable. It's even more interpretable than linear regression models. So based on color-coded salaries, it seems that years is most important factor in determining salaries. So this makes perfect sense, right? For less experienced people, though, so it seems that the number of hits has no impact. All of them will have pretty much the same color, right? Among more experienced players, so we talked about this one, the one with more hits tends, well, this is among the more experienced ones, sorry, we're on the right side. Players with more hits tends to have higher salaries. So again, this is not surprising, we're talking about these guys, right? And as you can see, the model is very easy to display, interpret, and explain. So we like this, this property of decision trees. Okay. Now, let's talk about the details of the tree building process. So this is the algorithm that we're going to go over. We start with divide the feature space into J distinct and non-overlapping regions, right? Theoretically, these regions can be anything. They can be square, they can be circle, this can be trapezoid, whatever you name it. But for simplicity, we're going to work with boxes. In 2 dimension, we call it boxes. But just, I want you to be aware that when it comes to decision tree, theoretically, does not necessarily they need to be rectangles or boxes. They can be anything, any shape. For simplicity, we are just using boxes. For every observations that fall into the region Rj, let's say R1, R2, R3, we make the same prediction. This is key, right? So we made the same prediction, which is simply the average of the target value. So here, we have a bunch of salaries. Do you agree? Do you remember the color coders? So the average, we report the average. I call it Y bar 1. So the prediction in region 3 is going to be Y bar 3, and the prediction for region 2 is going to be Y bar 2. Does everyone follow? Okay. At the end of the day, your model is going to predict 3 numbers. 3 simple numbers. Whatever you pass to this model, the output is going to be either one of these 3 outputs, right? Okay. Then the goal is to find the boxes R1, R2, up until Rj that minimize the RSS. You're all familiar with the fact that what is minimizing RSS mean, right? So we're trying to minimize the RSS in any of these regions. So for example, I can calculate the yi minus y bar 3 here, square it. So this is a residual sum of square. I can calculate the yi minus y bar 1 to the power of 2. So this is for region 1. This is yi minus y bar 2 to the power of 2. So this is RSS in region 2, right? Then I need to add them up. So add one RSS, the second one, third one. You can take the average and then add the mean squared errors, right? So I have one mean squared error here, one mean squared error here, and one mean squared here. And the goal is to minimize this summation. Is the objective function clear? Okay. So we talked about y hat rj. So y hat rj is the mean target value in the trained set for the jth box or rectangle. Okay. So with that, let's continue. So the algorithm is going to do this job. So we know what's the job. The job is to minimize the sum of these RSS or the mean squared errors, right? So that's the job. Now let's see how the algorithm mathematically does that. How does the algorithm select xj, select the feature, those two questions, and then put the cutoff, right? So those were the two questions. So the algorithm is going to do the job by something called recursive binary splitting process, right? So this is basically what the decision tree, both for decision tree and regression tree and classification tree, the process is called recursive binary splitting. So let's see what is that recursive binary splitting. So xj and s are selected such that, again, the goal is what feature to start with, where to put the split. They're selected such that splitting the feature space into two regions. Let's say x less than, let's call it s, xj less than s, and xj greater than s, right? So region left, region right. Let's call them 1, 2. So it's going to do the job that leads to the largest possible reduction in RSS, right? So let's start with this one. Let's actually move down. So these are the regions that we define, R1, R2. Are we good in terms of R1, R2? Okay. Now the algorithm is going to basically solve this optimization, minimize this over what? Over j and s, right? So j is the feature that I'm going to pick, and s is the split, right? So let's say we start from here. We start from there, right? So this is going to be, anything to the left is going to be my R1. Anything to the right is going to be my R2. I can go ahead and calculate the MSE here. Call it MSE1 or RSS1, it really doesn't matter. If you divide by the n, you get it. And MSE2, right? And then I add them up. Let's say I get 100. This is a number. I'm just making some numbers, right? Are we good? And then the algorithm is going to shift this split to the left or right. So this is one option. So for example, it's going to make this one and come up with the MSE. Let me see if I can use another color. So this is a second split. So I have MSE1, and then I have MSE2. Are you following? Okay. So if I add these two, maybe I get 50. So far, I know that this split is better than this. Does that make sense? And it's not only for the cutoff point, it's going to go over all the features. So maybe I make something like this. Then I calculate the MSE1, MSE2, and then add them up too. Maybe I get a number around 150. So the algorithm is going to go over all the combinations between features and where to put the cutoff points. And basically this optimization is solving over those two things, right? And at the end of the day, you will pick the one which produced the smallest summation of these RSS. Does that make sense? So this is how the algorithm is doing the job. And it's very powerful. Don't worry about the, I think Grayson asked a question, should we be worried about the computation limitation when it comes to large data sets? The answer is, it depends. What do we call large data set? But if, for example, if you're talking about a couple of 100,000 observations, decision trees are super fast because RSS, look at that, we have closed form solution. It's really easy for a computer to do this computation. But if you're talking about millions of records of data or terabytes of data, which in many applications we do, then not only the decision tree, none of the machine learning algorithm is going to work, basically. So usually what we do, we do parallel processing. So for example, you split the data into hundreds of subsamples, and you calculate, you make a decision tree for any of them, and then it's ensemble method in a way that we are using the same model, but using over the different samples. So it's ensemble method. But it's not specific to decision trees only. Okay, for any machine learning, if you're dealing with terabytes of data, you cannot use. You have to do parallel processing. All right. So that was for the regression one. And this, guys, this is important. we say that the best split is made at that particular step rather than looking ahead and picking a split that will lead to a better tree in some future step. So this recursive binary splitting process is what we call a top-down greedy algorithm. It is top-down because we start from the entire data set and we go down the tree. So this is top-down. And this is also called greedy algorithm. What does greedy algorithm means? This is what we mean. At each step, the algorithm is not going to look ahead. It's look at this, what do we get if I pick this split? And that's it. The algorithm is done with the calculation. Do not look ahead for the future split. So this is one caveat. We have to deal with this caveat for decision trees. Okay. And again, just remember that the recursive binary splitting process is called, also we refer to them as top-down greedy algorithm. Okay. So next, the algorithm is going to repeat this process, looking for the best feature and best split in order to split the data further to minimize the RSS. So we know that. So for example, if I have two regions and I look at the region number one and then make some subsplit, some extra splits. We continue this process until a stopping criteria is reached. That stopping criteria can be anything. Actually, we will talk about the hyperparameters of the model, but one of them is, for example, the number of observations in the leaf, in the terminal node, right? So you want to make sure that at least there are, I don't know, at least there are 30 observations in your terminal node. If that's your stopping criteria, the algorithm is not going to continue splitting the data. Does that make sense? Because if I go ahead and split the data further here, maybe at the end of the day, what is this? This is here less than 5. Maybe at the end of the day, I do something like this. I come up with a region that the observation is less than 10, and this is not good. Right? I wanted to have observations more than 20, more than 30, whatever. So this is a stopping criteria. Okay. So yeah, that was actually the algorithm behind regression trees. Here's another example. Imagine we have 5 region example, and we have x1, x2. These are the cutoff points, t1, t3, and t2. And you can, I want you to just think of it as an extra example, how we go from this two-dimensional and make a decision tree. So for example, we start with x1, if x1 is less than t1. So here, if the answer is no, we look at x2. So if here's no, here's yes. Then if x2 is less than t2, then you're in region 1. Is everybody following? So this is how we go through the decision tree. And this is very beautiful, actually. No, if I want to look at the perspective plot of the predictions for the regression, right? So this is how it's going to look like at the end of the day. Oh, by the way, let me ask you a bunch of questions here. So what is the level in this example? Go from the root node to the terminal. So how many levels do we have? It's 1, 2, 3, right? We have 3 levels.
So you don't count the top one?
That's the root, right? That's the entire data, right?
Okay.
Because let's say if this is the entire data set, if I start at the root, and then if I don't go down further, there's nothing. There's level is 0, right? There's no tree. Okay. So if I have, so at most, how many terminal values can I have if I have 3 levels? At most, how many terminal values can I have? 2 to the power of 3, right? This is binary, 2 to the power of 3, 8. Right? So at most we can have a tree, let's say 1, 2, 3, 4, 5, 6, 7, 8. Do you see that? If I continue splitting the data. So at most we are going to have 8 piecewise constant functions. So guys, this is our f hat of x. This is what at the end of the day the model is predicting, right? The algorithm is predicting. This is my f hat of x. And as you can see, this is super flexible. Do you see that? Let's find one of them. So for example, x2 is greater than, can you label this one for me? What r is that? R what? x1 is less than something and x2 is greater than something. What is that? No, x1 is less than something. So we are here. And then x2 is greater than something. So we are here. So this is our R2. See that? So this is R2. You can, at home, you can give it a try and see, for example, we have R2 or something, and etc. How many of these R's I have? 5 of them, right? And so the point that I'm trying to make here is that this f hat of x is super flexible. If I go ahead and continue splitting the tree, that at the end of the day, at each node, there's only one observation. This is going to be perfectly flexible. If I break down this tree to, let's say, at the end of the day, there's only one observation in the terminal nodes. What is the RSS? 0. 0. Does that make sense? So as you can see, decision trees can easily overfit the data. So we have to either make a stopping criteria or come up with some penalized version, right? So this is one disadvantage of decision tree. If you want to compare it with linear regression, so if I use linear regression, let me see how can I visually show that. This is a hyperplane if I use linear regression. Can you see that? Right? Do you think that the RSS, if I use linear regression, converges to 0? No. This is one of the advantages of linear regression because because the model is parametric, you're imposing some restrictions on the functional form. The RSS cannot go to 0. There's always been, as long as the data is noisy, there's always that irreducible part that we talked about in the first class. But in decision tree, in KNN, that irreducible part can go to 0 in train set. Okay, so these are something that I believe that you should know. And so now let's move on to the classifications. So are we good with the regression trees? This is how the regression tree, how the algorithm is doing the job. Now let's talk about classification trees. So the classification trees are very similar to regression trees, except for the fact that they predict a qualitative response rather than a quantitative one. And the predictions, the outputs are basically the category with most commonly occurring class, right? So let's say, for example, in region 1, we talked about this one. In region 1, what is the output? Blue. In region 2, what's the output? Blue. In region 3, what's the output? Red. Okay, so here is a very interesting question. What do you think? Do you think that out of the decision trees for classifications, can we get probabilities as outputs? Look at this data. Yeah, we can, right? So for example, look at that. What's the probability of, so we have 10 observations here. What's the probability of red? 1/10. What's the probability of blue? 9/10, right? So this is, again, another advantage of decision trees in general. Remember, in SVMs, we could not use probabilities. We could not report the ROC, AUC, but here we can. So we can play around with that threshold. Yep.
Aren't the probabilities how you calculate entropy and...
Oh, yeah, exactly. Yeah. But I want you to be aware that KNN, we can do probabilities. Logistic regression, the outputs can be probabilities. SVM, no. Decision trees, yes. Okay. So you can play around with that threshold. So you can report that ROC curve and AUC number. Okay, now let's go back to the fun part of the details of classification trees. Okay, so just as in the regression setting, the recursive binary splitting is used to grow a tree, right? So we are going to use our greedy top-down algorithm again. However, instead of RSS, we're going to use one of the followings. So what are these ones? Classification error rate, Gini index, cross entropy. You're all familiar with, at least with the concept of these three things. Here is another formulation for them. It's not that different. So we call them, so for example, in Gini, we showed 1 minus summation of pi to the power of 2. This is exactly the same as this. If you open up this equation and look, for example, if I have two probable, let's say probability of class red P, probability of class blue Q. So right, I get 1 minus P square minus Q square. Here, if you do that, summation of P multiply 1 minus P plus Q multiply 1 minus Q, you get exactly the same thing. I just wanted to show that this is exactly the same. But notation-wise, I really like this one because it's less confusing. So what are the P of M hat and P hat of MK? This represents the proportion of training observation in the mth region. So you can see the region. So for example, probability of class blue in region 1, probability of class red in region 2. All right, so this is K is class, M is region. All right, now classification error rate is not sufficiently sensitive to node purity right? For that reason, in practice, we're going to work either with Gini or cross entropy. So this is important, guys. I want you to remember that, as you can see, compare the classification error rate versus Gini and entropy. Here, you can say the slope is changing a lot more compared to here, right? So it's more sensitive to changes. And what we care in classification regression, in classification trees, is that how the impurity changed when I made this new split. So what was the impurity before the split? What's the impurity after the split? Then compare. So what is my information gain? What was the value added of that split? What is the information that split added on the table? So we call it information gain. Okay. So let's see if we can finish this example in 5 minutes, and then we're going to stop here. So this is what I was planning to do. Yeah, we can stop there. Okay, so let's say, I'm going to ask you a bunch of questions down the road. So let's say that's the data, right? So the data has 10 red circles. Let me write them down. So 10 reds and 20 blues. 20 blues. Okay. And I'm going to calculate Gini index, cross entropy, and error rate in either case, right? So let's start with the entire training data set before making any split, right? So let's start with the error rate. The error rate is the easiest. So if I have 10 reds, 20 blues, what's the probability, what's the error rate if I'm looking at the red ones? 2/3, right? So you can think of it as probability, right? 2/3. What's the probability of making prediction blue? 1/3, right? What's the 1 minus maximum of them? So 1 minus max of 1030 or 2030 is going to be 0.333. Is this clear? Okay, so again, this is our classification error. It depends on what error rate you want, what class you're looking at. If you look at class blue, what's the error rate? 1/3. If you look at class red, what's the error rate? 2/3. Does that make sense? And then in terms of for the combination, we report the 1 minus max of those things because we want to get the minimum error rate, right? So this is the error rate. When it comes to Gini, so look at that. If I do not do the split, let's calculate. This is a guys, remember what was PJ? Probability of class, let's say K in region M. So I can think of it as PMK. Probability of class K in region M. Here, there's only one region. Does everyone see that? So what's the probability? So I do 1 minus the summation of those probabilities. What is the probability of red? 10/30. I have 10 reds and 30. What's the probability of blue? 20/30. Are we good? So this is going to be my Gini number for that region, only one region. Okay? Let's do the entropy. For entropy, well, this is actually called cross entropy because the log is natural log. It's not to the base of 2. So when you use the natural log, we call it cross entropy. Okay, so let's calculate that number minus summation of the probabilities, right? So we know the probabilities 1/3 and 2/3. So 1/3 multiply log of 1/3 plus 2/3 multiply log of 2/3. And if I would put a negative sign, I get this number. Is this clear how we calculate the Gini and the entropy? Okay, now let's move on. Just bear with me 2 more minutes. Now I'm going to make 2 splits. This is the vertical one. The next one is going to be the horizontal one. And if I ask you which one is a better one, actually, it may be a close call. Do you agree? So for that reason, we have to trust the numbers. So let's see. So if I want to talk about, so I have 2 regions. Let's call them region 1, region 2. The error rate, we can start from here. So on the left, we have, sorry. Well, let's start with the Gini. We go from left to right. So 20 observations on the left, 10 observations on the right. So what are the weights of the regions themselves? 20/30, 10/30. Are you following? Then I have to calculate the Gini of this region multiplied by 20/30. Gini of this region multiplied by 10/30. That's going to be the overall Gini. Does that make sense? So let's do that. 20/30 multiplied the Gini of the left area, the region 1. So for region 1, what's the probability of blue? I have 20 observations here. How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. So what's the probability of red? 9/20. 9/20. What's the probability of blue? 11/20. Then I multiply by this weight. Are we good? Then I go ahead. Region 2, what's the probability of red? Does everyone see that it's 1/10? I have 10 observations on the right. What's the probability of blue? 9/10. I add these two, I get 0.39, right? For entropy, the probabilities are exactly the same, but the formula is different, but I get 0.57. For error rate, weight is 2/30. The classification 9/20, right? 9 red over 20. Because remember, we look at the minimum of the error, right? 9/20 is smaller than 11/20. And here, 10/30 multiply 1/10, because that's a minimum of 1/10 and 9/10, right? Or 1 minus maximum or the minimum. So I get to, so the number is 0.333. I want you to do the last one as an exercise and calculate these numbers. So we have 15 observations on the top, 15 observations on the down at the bottom. And so these are the weights, 15/30. What's the probability of red? 2/15. Does everyone see that? The blue, 13/15. Okay. If you do the math, we get 0.37, 0.54, 0.3. So what I want you to pay attention is that, so at the end of the day, by the way, answer this question by looking at these numbers, these green and red numbers. Which split is better, vertical or horizontal? The algorithm is looking for the one with the minimum impurity index. Which one is the smaller? The green ones. Well, not between them.
Oh,
Between Gini and cross entropy and error rate, well, actually, you can pick any of them. If you pick any of them, this split, this one, the horizontal split is outperforming the vertical split. Does that make sense? So the algorithm is going to pick this split, the horizontal split. So far, so good. But I don't care about the error rate, because look at that. Do you see 0.33, 0.33, 0.3? It's not that sensitive to impurity. But compare these ones, 0.64, 0.57, 0.54, and 0.44, 0.39, and 0.37. This is more sensitive than this, than this. Does that make sense numerically?
So the vertical line is a plus one.
Yeah, the vertical line is what the algorithm is going to pick.
And
Okay.
is that for both regression and classification?
For regression, we do MSE.
Oh, okay.
This is classification. We come up with different criteria, right? Yeah, that's pretty much it. So, oh yeah, I'm already over time. So I will start from this slide next class, and then we talk about pruning a tree and how do we tune hyperparameters. Okay. All right. Thanks so much. See you on Wednesday.
For regression, is it just MSC, or can you do MSC plus these three?
Oh no, it's just MSC, because MSC is doing a perfect job, right? So let me pause the recording.